Brandon, what's up? I'm making this video. It's like my last 48 hours of this trip, so kind of plans are getting shifted around because there's stuff that I've been trying to do that couldn't do one day, and now it turns out I can do a different day. So unfortunately, that means this day is kind of unsettled as of right now. So I'm going to make you this video and a couple of other shorter ones just about these basic topics so that you're not without any help. Hopefully your teacher does answer your questions, but if not, just text me anything specific, and I'll, at least when I get back, whenever that is, I'll have them, and I'll put them up here as well on YouTube, okay? So, formal charge. When we last talked, I asked you a question, I remember. Have you heard guys talked about formal charge, and you said no, and I said, that's it, I'm not going to even mention it. Although I had a feeling it was coming next, and it turns out that's what was coming next. So when you're doing Lewis structures, it's very simple if the molecules are simple, okay? Just put whatever the lone guy is. There's only one oxygen. Okay, put it in the middle. It's all good. Put all the electrons around the outside. Bond appropriately. Okay. Then you get some that seem obvious but aren't, as is the case like in math and in science all the time. There's always exceptions, right? So we got to dig a little bit deeper, and that's where formal charge comes in. So the molecule that I mentioned to you was this bad boy right here, dinitrogen monoxide. Now, the old school typical way, old school being like pre-Thanksgiving basically, the old school way of doing this guy, Lewis dot structure style, was the following. Well, there's only one oxygen, so it probably goes in the middle. The two nitrogens go on the outside, and then I'll just make sure the bonds match, everything's happy, so I'd get something like this. I'd get something like that with oxygen in the middle. I'd be cool because I think there's only one oxygen. It's got to go in the middle. I would remember, like, hey, Zach told me this funny little recipe for doing the Lewis dot structures. I'd count the valence electrons total first. Well, each nitrogen has 5, so 5, 10, because 5 and 5 is 10, and oxygen has 6, so that's a total of 16 valence electrons that I have that are going to be represented in this Lewis dot diagram structure. Okay, 2 electrons per bond, so -2, -2, total -4 off the 16. I got 12 left. Well, where do those 12 go? We got to make sure the outside guys are happy first, so that means the nitrogen. So 1, 2, 3, 4, 5, 6 there. 1, 2, 3, 4, 5, 6 there, a total of 12. Hey, no more valence electrons left. I'm happy. Nitrogens are happy. Oxygen is not happy because it's only got 4. So remember, like we talked about last time with the honk rule, hydrogen, 1 bond, or as your teacher likes to call it, 1 electron domain, 1 ED. Oxygen has 2 EDs. Nitrogen has 3 EDs, and carbon has 4 EDs. So HONC, 1, 2, 3, 4 electron domains. That doesn't mean that they can't form a whole bunch of bonds in those domains, though. So check this out. I say oxygen's not yet happy. I can take any 2. I'll just symmetrically do it like this. Any 2 electrons and make it into a second bond right there. And similarly with the other side, boom. Now, dinitrogen monoxide looks happy. It looks great. 8 electrons are on the nitrogen, 2, 4, 6, 8. 2, 4, 6, 8. Both nitrogens are cool. 2, 4, 6, 8. The oxygen is cool. And this seems to be good. Seems to be perfect, seems to be wonderful. I seem to be done. I'm not done. Why I'm not done is because now I have to consider some formal charge. Okay? I want to calculate the formal charges on each of these guys. And all formal charge is how many valence electrons does this certain atom usually have, and how many electrons are currently around it, electrons or bonds. Okay? And we combine those. So, for nitrogen, normally it's got 5 valence electrons, right? But how many just items do I see around it? 1, 2, 3, 4, 5, 6. I subtract those 6, and I'll just put the -1 beneath it. Okay? So right now this nitrogen has a formal charge of -1. Awesome. Doesn't mean anything yet, but I know that this nitrogen over here is going to have the same thing. because it's got the same exact scenario. It's got a total of 5 valence electrons, but 6 items around it. So 5 minus 6 is a -1 right there. And the central oxygen should have 6 valence electrons, but right now it's got 1, 2, 3, 4 items around it, bonds and or dots for electrons. So I say 6 minus 4, and right now oxygen's formal charge is 2. So can I do better? Now doing better means, can I get these, even though these add up to 0, it's not really about what they add up to, it's like, can I drop this guy, or actually raise this guy, drop this guy, raise this guy, can I get them all closer to 0? That's what I want, okay? That's the way I was taught, but who cares what I was taught, because it's how your teacher is teaching it. And she came up in one of her slides, you want the most electronegative of the guys here to have the smallest, the most negative, or the least positive formal charge. Well, right now, the most electronegative atom out of these two, nitrogen and oxygen, is oxygen. And right now, that's got a pretty big positive number there. We don't want that. So if you think about it my way, I want these guys all kind of close to 0 if possible. Or your teacher's way, which is I want the most electronegative guy, the guy in the most upper right of the table, oxygen, to have the smallest possible number here. Probably we could do better. So what if I say, instead of oxygen in the middle, now I'm going to put one of the nitrogens in the middle. So I do this. Or I could set it up like this. Okay, same 16. Original starting valence electrons. Because remember, there's 5 here, 6 here, total of 16. Take 2 away, take 2 more away. So now I'm dealing with 12. I do the same thing. I put 6 around this outside nitrogen. I put 6 around this outside oxygen. That's going to take care of all the valence electrons. So now I get something like this. Okay, and just like before, because nitrogen can form up to 3 bonds, a triple bond, right? And it's got 3 bonding domains, I can make each of these into a double bond for the central nitrogen. So, now, is this any better than that diagram? Let's find out using formal charge. Nitrogen starts off with 5 valence electrons, minus 1, 2, 3, 4, 5, 6 items around it. So okay, nitrogen still got a -1 if it's on an outside of the molecule. This nitrogen I'm going to save, but let's see if oxygen changed from a +2. Oxygen starts with 6, 1, 2, 3, 4, 5, 6. So check that out. Oxygen, the most electronegative atom in the mix, started off in this diagram with a formal charge of 2. Now it's got a formal charge of 0. Remember, 6 valence electrons originally for oxygen before I even do the diagram. Then, in this setup, 1, 2. That wasn't fully erased, but it should have been. 1, 2 valence electrons. 3, 4 valence electrons. 5, 6 for the 2 bonds there. I start with 6. I take away 6 items around it. I'm left with 0. I like that a lot better than a 2 formal charge because it is more negative. It's less positive. Either way is good. So now, what's up with this guy? Nitrogen starts with 5 valence electrons, minus 1, 2, 3, 4 items around it. So, whether you use your teacher's way or my way, hey, I start off with -1, 2, and -1. These numbers, overall, they're closer to 0. I actually have a 0 here, and the 2 is no more, and I have 2 1s. But the 2 went to a 0. I like that. Numbers are overall closer to 0. Your teacher likes it because the oxygen, the most electronegative atom, has dropped its formal charge from +2 to 0, made it more negative. That's the key with formal charge. Therefore, this would be the appropriate diagram right here for dinitrogen monoxide. Now, using, you can pause this video a little bit if you want to just rewind it. If I was talking too fast, I just want to make this short. I want to get it all in. So, in your notes, you had NCS, the thiocyanate ion, NCS minus, in fact. So, let's see. This is going to be the diagram, okay? This is going to be the diagram because it can form the most bonds. Remember, carbon, the Hank rule, can have 4 bonding locations. That's my language, or your teacher can have 4 electron domains. So, not just because it's written NCS, but carbon can form the most bonds around it. So it's a good choice to try it in the middle. So you in your notes came up with 3 possible options for it. Try to fit these all in. Okay. Now, how many valence electrons total are there? 5 and 4 makes 9. And 6 makes 15. Ew, but it's an ion. 1 more electron makes 16. So again, we're dealing with 16 electrons. So it's going to look a lot like dinitrogen monoxide, like what we just did. We're going to start with 16 total valence electrons. Okay, 2 bonds in each. 2 electrons in each bond. Drop the total to 12 in each of these guys. Put the 6 around here, put the 6 around here, and this N, and this S, and this N, and this S. Gonna knock out those 12. We're gonna have all the valence electrons taken care of. Just gonna put those all on there. Boom, we got them all down. Now, there are many ways to draw this. 3 ways, in fact. 3's many, I guess. So remember, carbon can form 4 bonds or have 4 bonding locations or electron domains. It can form a couple of double bonds, or it can form a triple and a single. So we got to account for all those, okay? So let's try the double bond way, which is what N2O was. There's one option. Now, let's say I want to, remember from the Honk rule, nitrogen can form 3 bonds. So let's say I want a triple bond with a nitrogen. That means I'm going to take both of these guys, both of those electron pairs, and put them as bonds. Because again, we got to make carbon happy. Carbon wasn't happy yet, like this guy. He's only got 2 bonds, 4 total electrons. I got to get 8 around the central carbon. So I tried a triple bond here, left a single there, 2 double bonds here, or maybe I can, instead of a triple and a single, I can do a single and a triple. So I'll do a triple bond with the sulfur. Maybe that'll work. So now, how do I decide which one is which? Got to do the formal charge trick, okay? Just like last time. Because whenever there's ambiguity, whenever you're like, oh, it could be this, or it could be this, or it could be this, maybe there's a resonance, maybe it could be any of these guys, maybe they could all exist equally in nature, I don't know, we got to do formal charge. So, again, we want the most electronegative to have the smallest formal charge, and we want them all to be as close to 0 as possible. So that might be a better way to approach it if you forget at all which one's the most electronegative, because then that way, if anything's got super huge numbers in it, either positive or negative huge numbers, you just ignore it. Okay, so let's calculate the formal charges. Nitrogen 5 normally minus 1 2 3 4 5 6. So 5 minus 6 is negative 1. This nitrogen, we'll just do the nitrogens. 5 minus 1 2 3 4 5. It's pretty good. We got a 0 there. 5 minus 5 is 0. And this nitrogen over here, 5 minus 1, 2, 3, 4, 5, 6, 7. Ugh. That's going to be a negative 2. That's a big number. I'm probably not going to like that. But I'm not going to immediately rule it out, because maybe I get bigger numbers elsewhere. Okay? So these are my 3 formal charges on each nitrogen possibility right there. Next, the carbons. Carbon starts with 4 valence electrons, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. So the formal charge on any of these carbons is going to be 0. So that's good to know, because that way the central, it's just not going to change. So it's not going to depend on the formal charge of carbon. Just to save time, I just put the 0 here and the 0 here because they're all done the same way. Carbon, again, starts with 4 valence electrons. 1, 2, 3, 4 items around it in the diagram. The original 4 valence minus the 4 items around it, 0. Now, for sulfur. Sulfur originally, it's in the oxygen column, so it's going to have 6 valence electrons like oxygen does. 6 minus 1, 2, 3, 4, 5, 6 is 0. 6 minus 6 is 0. This guy's got a negative 1, 0, 0 setup. Those are very small numbers, very close to 0. I like that. This sulfur right here, it's going to start with 6 minus 1, 2, 3, 4, 5, 6, 7. So 6 minus 7 is negative 1. Uh-oh, we got a tie. We got 2 zeros and a negative 1 here, 2 zeros and a negative 1 here. This guy's got a positive 2. I'm already thinking I'm throwing that guy out, so I'm going to choose between these 2 guys on the left. But just for closure, 6 minus 1, 2, 3, 4, 5. 6 minus 5 is 1. So this guy with the 2, 2 is the biggest number anywhere. I would consider negative 2 equally as big as 2 because it's as far away from 0 as 2 is. So I'm going to ignore this possibility. It cannot be the sulfur triple bonded. And by the way, if sulfur is triple bonded, that seems weird because sulfur, I've never seen a triple bond, but maybe in your experience you have, but I haven't seen it. So I'm just going to get rid of that anyways. So there's a lot of evidence to get rid of the rightmost guy. How do I choose between 2 zeros and a negative 1? Well, we got to go to your teacher's rule. The most electronegative atom has the most negative formal charge. Well, of these three guys, what's the most electronegative? Well, it can't be sulfur because sulfur is the furthest down on the periodic table and electronegativity gets bigger up to the right. So I'm going to choose the two guys in the top row, carbon and nitrogen. So, of those two, carbon is here, nitrogen is immediately on its right. Nitrogen, therefore, is more electronegative, so it should have the smaller number. Here's my nitrogen. I got a negative 1. Here's this nitrogen. It's got a 0. Negative 1 is smaller than 0 or more negative than 0. Therefore, I'm going with this guy. That is the structure that I want. Okay? For the formal charge reason, combined with my reason, I want the numbers as close to 0 as possible in all ways. Okay? And if you keep the electronegativity aspect of it always in mind, it's a very, very useful technique to determine formal charge. So overall, to get that structure, all you would do to finalize it is do this. After all that, you still got to remember it's an ion. So you got to put the brackets around it and the minus charge. Okay, so that's part 1. That's formal charge. It's how you attack it.